Good evening, everyone. My name is Jaap Mengers, and I'm going to talk to you about a project I worked on recently. Let me start with a small introduction. I'm a software engineer at Q42, and Q42 is a tech agency. We're based in the Netherlands, in Amsterdam and The Hague. And we work for clients such as PostNL, which is the Dutch postal service. For them, we build the native iOS and Android apps that consumers use. But we also work for the Rijksmuseum. They have a lot of art, which they have up on their website, and the apps that we built for them in high resolution. And more recently, we launched the new iOS and Android apps for HEMA. The project that I'm going to be talking to you about today is called SenseMath. And SenseMath is a project we did together with the Royal Dutch Visio, or Visio for short. And they're a non-profit that work with people that are partially sighted or blind. And they deliver information and also services. And one of those services is education. There's 5 Visio schools, high schools in the Netherlands. But Visio also delivers content or resources to blind students in schools throughout the country. And you can imagine that some subjects might be more difficult to teach than others. Math is one of those subjects that's quite difficult to teach, and more specifically mathematical graphs. Paper is incredibly effective at communicating information, so drawing a line on paper or drawing a graph on paper can really easily communicate the shape of a function, and that's really a lot more difficult when you're blind. So there's some solutions to that currently. So one of those is swell paper, which is basically a relief that's printed on paper, very much like Braille, and where you as a student can touch the paper and can feel the line as it progresses from left to right. But there's also drawbacks to this. One of the obvious drawbacks is that this paper needs to be printed, which obviously takes time and is quite costly. So it doesn't allow for independent experimentation, which you might want to have when you're in an educational setting and want to play around with the concepts that you're learning. So Visio came to us with the hypothesis that sound could also be used to communicate the information that's in a graph. And they basically asked us to help us design an instrument, a sonic instrument that can compete with a line on paper. And we obviously were very excited to help with that. Since this was a project that we got involved with really at the start, we were also involved in trying to define, so what does this instrument need to look like? We started with what we call a jump start, which is basically a design sprint in which we try to tackle some of the technical challenges that are ahead early, so that we can validate in as little time as possible that it's actually possible to build something like that. So there were a couple of people involved in that jumpstart. Obviously, there were people from Visio, but also some of their blind colleagues that could help us with understanding the challenges that blind students face when they get to subjects like math in high school. But we also invited some math teachers, high school level math teachers, that could tell us the way that they teach these concepts to students, and also they could revamp our knowledge of high school level math, because for me it was a long time ago. Let me start with a small demo of the app that we built, so to give you a little context of what I'll be talking to you about in this talk. So here goes. So what you saw, and more importantly heard in this demo, is the core functionality of the app, which is you as a student or end user can put in a function, you can press play, and you can hear what that function sounds like. But you can also put in multiple functions and see where they interconnect. Is that the word? Where they cross. So that's the basic functionality of the app that we built. As I was thinking about or preparing this talk, I was thinking about the challenges that we faced, and I noticed there was a theme into going across all the things that we worked on, and that is that we're trying to build an instrument that can compete with a line on paper. So whatever we do, the most important thing is that this tool works correctly and works as fast as possible in communicating information. So that's the main subject. So to rephrase, this project is based upon the design principle that form follows function, also quite literally. And in this talk, the coming 30 or so minutes, I'm gonna talk to you through a couple of challenges that we faced based upon this design principle that form follows function, and I'll walk you through the challenges and the way that we solve them. So let's get started with part one and the first challenge. And that's, I think, the quite obvious. The most important thing again is to have audio that can communicate the information that's in a graph. And we all had ideas about what that should look like or what that should sound like. But we also had to do a lot of testing, obviously, with end users to see what would work best in different scenarios. So a lot of that work was playing around with sound. We had the fortunate situation of a colleague having just joined us who had graduated just before in a bachelor's in sound design and sonic interaction design. So that was a perfect fit, and he brought to the table a lot of knowledge about sound and the way that it can be used to communicate information. So he started off working on tons of different sounds, making .wav files and sending them to us so that they could be tested with blind students, because that's, as I said, the most important thing. At the start of this project, so the jumpstart I mentioned, this was in pre-COVID times, so it could be done at our offices, in this case in Amsterdam. So, and what you see on this picture are Jesse and Lise. They work with Visio and they're blind themselves, and they could already really help us with experiencing the app and telling from their perspective how effective it was in communicating this data, this information. What we also did in this first design sprint kind of week is we went to schools with the sounds that we had, and we tested a bunch of them to try and get a feel for how effective they were in communicating the information. So that obviously was the main part. So how good can it transfer information? But we also wanted to know things like how quickly does it get annoying, and how much detail can you hear when we take instrument A versus instrument B. So that was the first challenge that we worked on, was really getting the sound right. And that was an ongoing thing throughout the project. As we were building the app, we continually tinkered around with the sound and put it in front of users, got their feedback and adapted. Then the second part is one that I hadn't foreseen when we started the project, but that turned out to be quite an interesting thing. Because the main interface that users will be using with our app is VoiceOver. It's nice that there's a graphical user interface for developers like me and for the teachers that might not be blind. But the end users, in this case, we know are all blind or partially sighted. So they will probably use some assistive tools like VoiceOver. And one of the things that I hadn't considered was that when we talk about math and talk about a mathematical function, we use different language than we might if we would just spell out the characters that are in a function. I'll illustrate this with a short little demo again.
Heading. Edit. Button. Two functions. Heading. Y equals x caret 2 3. Linear. Include function in playback. Switch button. On. Y equals x caret 3. Linear display.
So what you saw in this video is me going through the app with VoiceOver on. I also included a little video of the VoiceOver gestures that I used. And what you can hear is that while VoiceOver does its best at communicating what the function is, so y equals x caret 2 minus 3. It isn't the way that a teacher would talk about this kind of function to a student. A teacher would say y equals x squared minus 3. And this is really a topic that we had to investigate as to how we could fix it. We quickly noticed that Apple itself had fixed it in their Pages and Numbers app. So here's a small demo of what that sounds like.
Equation preview. X squared minus 3. Maths. Right equation. Text field. Is editing. X caret 2 3. Character mode. Insertion point at end.
So what you hear and see is an equation mode that's in Pages, and apparently iOS can understand an equation and can also use VoiceOver to correctly spell out the function in terms that a teacher would use. So we set out to see if we could also use this equation view that iOS natively has in our own app. Sadly, that wasn't the case. What we did find out is that this equation view supports MathML, and MathML is a web standard, and it's intended to facilitate, I'll quote it, to facilitate the use and reuse of mathematical and scientific content on the web, and for other applications such as computer algebra systems, print typesetting, and voice synthesis. And the last part is the part that we're interested in. So we figured if we can use MathML in some shape or form, then we don't have to synthesize our own VoiceOver text, which would involve us going through the equation, trying to figure out what's going on in it, and then converting that to either English or Dutch text. We support English and Dutch, because that would be a different project altogether with the range of function that we would want to support in the future. So we ventured out to see, can we use MathML? But before I'll talk to you about that, let me first explain a little bit what MathML is. So it's an XML format that you can use to express a function. So what you see on the left side is a function x squared plus 4x plus 4 equals 0. And on the right side is some markup that you could use to express that function. But here also we had the difficulty of how can we parse this function that you see on the left, which is maybe doable, but a function can get infinitely complex, and we don't want to build a parser that can understand all that. So how do we go from what's on the left to what's on the right? And this is where MathJax comes in. MathJax is a bit of software that you can use in your browser, so it's JavaScript based, and it'll do exactly that. It'll take a function just as a string, and it will return the MathML that can be used. So now we have a couple of most of the things that we need to support rich voiceover of our function, but we need also a way to play it. And as I said, the native iOS equation isn't something we can use in our app. So what we ended up with is just adding a WK web view to the app on all places that we wanted to show an equation. And this is far from ideal, I'll admit, but it works. So I'll show you a little demo of what we can do if we add a web view with MathML in it, and what that does to VoiceOver.
Graph number 1. Heading. Edit. Button. 2 functions. Heading. Use y equals x squared minus 3. Maths. Include function in playback. Switch button. On. Y equals x cubed. Maths.
So what you see here is basically the same thing as the equation view that you saw before. We managed to get the styling of the web view. So the web view is there's 2 web views on this page. It's the first function y equals x squared minus 3, and the second function y equals x cubed. We managed to get the styling good enough, and we managed to get a voiceover working. So you saw me swiping through the app, and it got focus, and voiceover was able to pronounce the function in a sensible way. We ended up adding both this view and the linear view, as we call it, which is basically just the string representation, because there's Braille readers that you can also connect to your iPhone, and they do understand the linear view, but they don't understand MathML. So we need to support both of them, and then a user can determine: do I want to use the rich view or the rich voiceover experience, or do I want to have the linear view, which my Braille reader understands? So that was a little bit tricky, but we got it working. So on to the next challenge, which is the voiceover UX. I've developed quite a lot of iOS apps in my time, and when it comes to accessibility, I'll usually do the low-hanging fruits and the things that I learned from the internet in terms of what you should do, so to correctly label controls and stuff like that. While we were in this project, we worked together with Jesse and Lisa, I mentioned before, to really go a step beyond that, and to really optimize for an optimal voiceover user experience. And a couple of the things that we put in the app and that we learned from them, I'll show to you right now. And the first one is called the Magic Tap. This is something I didn't know about, but most apps that play audio or video or whatever, you can use a 2-finger double tap to play the audio. So it will work in Spotify, for example, or in the podcasts app. So users that blind users that use an app that plays audio or video might expect to be able to double tap to start playing the audio. So that's the first thing that we added. That's the Magic Tap accessibility action. This is a little bit of code. There won't be a lot of code in this talk, sadly. A little bit of code in how we did that in our SwiftUI app, and what that then looks and sounds like is this.
Play graph button. Tap twice with 2 fingers to start and stop playback. Use the rotor to access steps on x-axis, maxima and minima, intersections between graphs, below the x-axis.
So what you see in this demo is me giving focus to the play button, where we added accessibility labels to hint users to the existence of this Magic Tap functionality. Currently, the play button has focus, as you can see. Well, there's a little bit of a bug, it seems, in iOS where the focus isn't correctly lined up with the control that it's focused. So the play button is in focus, so I could just tap it with one finger, double tap it with one finger to activate. But the thing with Magic Tap is that you can use it throughout the app, wherever, regardless of which control has focus. And that's obviously a nice thing. You want to be able to just quickly start and stop the audio without trying to find the play and stop button before doing so. So that's the first optimization we did. The other one was also briefly mentioned just now by VoiceOver, which is the VoiceOver rotor, which I myself hadn't heard about before I started this project. And what it basically is a quick dial menu with some features that your users might want to access often in your app, and without them needing to go through a whole load of menus and stuff like that. So I'll first show a little bit of the code that we added to make that work, and then I'll give you a demo of what that looks and sounds like. So what we do here is we go down to UIKit. So we, as we were working on a lot of this accessibility stuff, we also found out that some things aren't yet, they might by now, but weren't yet available from SwiftUI. So the VoiceOver rotor is one of those examples that we couldn't customize from SwiftUI, it seemed. So what we do here is we go down to UIKit, have a view controller, and in the view controller we can set accessibility custom rotors. And we have a bunch of them. I'm showing here on the slide just one, which is the steps on x-axis. Those are the little ticks that you hear when playback is started. We wanted to be able for the user to quickly be able to toggle whether they want to hear those ticks or not. We also have it tucked away in a little menu somewhere, but this is one of the things that we, together with the crossings with other functions and the minima and maxima, we want to be able for a user to quickly toggle those to sound to more or less zoom in on a bit of the function. So if you just want to hear the shape of the function, then you would disable all other sounds and just get a feel for how it progresses over time. But then if you want to know, okay, so how does it interact with other functions that are in here, you also might want to have the intersections with the other graphs. And if you want to get a feel for, so where's the how much minima and maxima does this function have, then you would enable that. So this is how we added to the accessibility custom rotors array. And also what you see here is that we post custom announcements to UI accessibility, and this will cause VoiceOver to announce whatever string we give it. So that in action looks like this.
Maxima and minima. Intersections between maxima and minima. Steps on x-axis. Steps on x-axis. Off. Steps on x-axis. On.
So what you saw in this demo is me using this dial kind of gesture, which triggers the rotor when VoiceOver is enabled. And I could go through it till I ended up with the action that I wanted to toggle. Then swiping it would toggle it. What you also saw me use is the double finger magic tap action to start and stop again. So this is I think a brief demo of how a VoiceOver user might use this app versus a non-VoiceOver user that would go through the menu and enable these things. So with just these rotor and magic tap actions, they can control what they want to hear when they press play. Then on to some VoiceOver shortcuts. So what you're seeing right now on the screen is, I'll replay it a little bit, is how you can change the speed in the app. So that's the playback speed that you can control. It's a little speedometer icon on the left that you as a sighted user might use, which opens a slider that you can use to change the speed. And if we would do nothing, then VoiceOver would work the same way. So you'd give the speedometer button focus, then tap to click it. Then the slider would appear. You would need to find focus on that element, and then you could go through it. And one of the things that came up when we were discussing this with Jesse and Lise was that for a sighted user, it makes sense to hide the control initially, because there's only so much screen real estate. But it doesn't really make sense for a VoiceOver user to have this this interaction of showing and hiding elements on the screen. What they suggested is, could we just give the speedometer button that's already on the screen, have that control the speed directly? So that looks a little bit like this. So the actual slider that is on the screen when we toggle the button is hidden for VoiceOver. So VoiceOver you don't see it or hear it more correctly. And then also we added an accessibility adjustable action to the button, the speedometer button itself, in which we capture adjustments gestures. So we grab the direction and we change the playback speed accordingly. I'll also give a demo of what that then looks like for a VoiceOver user.
Playback speed 110%, but 120%, 130%, 100%, 190%, 200%. One hundred, 90%, 80%, 70%, 60%, 50%.
So what you saw in this demo was again an optimization of the UX specifically for VoiceOver users, which we knew to be the primary users of our app. So I think all these adjustments taken together make it a better user experience than it would have been initially if I would just have added accessibility labels to everything. So for me, the main takeaway here was that it was very valuable to work with Jesse and Lise, but with more specifically with VoiceOver users that know the patterns that work well and know also the patterns that don't work well. I didn't have any intuition with regards to these things. So a lot of the times I would be working with one of the colleagues at Q42 and trying to figure out, okay, how shall we design this in terms of controls? And then we would build something, and then afterwards, when we were discussing with them, they came up with solutions that I wouldn't have thought to be either usable or obvious or whatever. So the main takeaway here is to really test with people that use this day in and day out. On to the last form follows function part of this talk, and that is the math input. And here we have a similar problem that we also had with speaking or having VoiceOver correctly tell us what the equation looks like. Because we also need to be able to input an expression, and there we also have a lot of mathy things going on. We have some letters that do occur, but we also have numbers. We have operators and stuff like that, and we don't have that in a normal keyboard. So the first approach that we took was to have a UI accessory view above the keyboard. You might have seen those or built those yourself, where we would put in all the operators that we deemed necessary for a high school math student to be able to enter. But quickly we realized that the VoiceOver experience for that UI accessory view was not optimal. So we could work with it, but we started considering, should we build a custom keyboard? And I think we were quite hesitant to do so, but in the end it worked out correctly. Let me first show you a little demo of what that ended up like.
Cos, tan, log, sqrt. L at caret x variable 7 x variable x atom caret 7 2 3 star hyphen Kapeltiken x caret 3 slash 3 3.
So there's a lot going on in this video. There's some kind of VoiceOver bug that I can't really place where it would use the Dutch voice for things like to and Kapelteken. But what you see here is me browsing over the screen with my finger to try and find the controls that I'm looking for. So I was trying to enter an equation here, x squared minus 3. And as we were building this, we had a lot of discussion on, okay, how do we want to group the items in this keyboard? So right now the keyboards start with some operators that you might not really use a lot, like sine, cosine, stuff like that. You probably use the numbers and x and squared and stuff like that way more than that. So our intuition was to put those in front. But here again, as we started talking with Jesse and Lise, they mentioned that there was different ways of using a keyboard, and one was the way that I just showed, where you just drag your finger across the screen and try to find the input that you're looking for. And that's not just necessarily in a keyboard, but you could also have that when you're opening an app and trying to find out what the kind of features you have on the screen. So their advice was to not really focus on trying to get the order right. So obviously it needs to work correctly, but to make sure that it was a complete keyboard. So in the end, we ended up talking more to the math teachers that could, from their experience and knowing the curriculum, tell us, okay, you do need this in here. So sine and cosine, but also square root, for example. And you don't need this, so we asked them. So can you give us the list of everything that should be in there? And the voiceover experience wasn't really an issue, it seems, at least to Jesse and Lise. So that was also, I think, an interesting thing that was counterintuitive to me. But in the end, I think this keyboard works. We have to test it, obviously, with our real users. But I think this won't be the biggest problem that we might have. Also, one of the things we were thinking about is we use a keyboard right now, but it could make sense for this app to use voice instructions, where you would enter an equation through your voice, which would be quite a lot easier maybe than trying to type them in on a keyboard. So that's a brief overview of stuff that we learned as we were developing this app. So where do we currently stand? We're working towards releasing the first version and to start testing that in class. A lot of the testing that we did right now was a little cumbersome in COVID times because we couldn't go to classrooms to work with students. So we, in the end, ended up using lookback software where it uses the screen recording API and it just sends over the screen. So we'd ask a student to install our test version of the app to start lookback, and then one of us could work with them and trying to work them through the testing phase of the app. Hopefully, we can go to some classrooms soon if the COVID measures allow it, to be able to test it directly with users. So yeah, releasing version 1, testing it, and then also there's plans already to start working on version 1.1, which will include a library of books that are commonly used. So the mathematical curriculum, the books that are in there, to go chapter by chapter, page by page, and exercise by exercise. To have students be able to use the SenseMath app to work through the book without having to input all the functions themselves. So hopefully I can give you an update about that at some point, and it will be a great success. But we'll have to wait and see. So that's everything I have for you today. Thanks for your attention. Do note we're hiring. So if you want to work on projects like these, then please get in touch, and hopefully see you next time. Thanks. All right, so thanks for watching. I'll be taking some questions now. There were 3 questions posted already. So I think Axel asked, would it help if the 2 graphs use different base frequencies? I think, Axel, what you probably mean by that is to put one of the questions on a low end of the frequency scale, and the other one of the functions, I mean, on the low end of the frequency scale, and one on the other end, a higher end of the frequency scale. So what we try to do is to have one octave for a function, and to have some similarity between functions. So one function A that would cover a specific range would range from a certain pitch level to another pitch level, and then another function that would be in the same pitch range would or would be in the same function range, I should say, would be in the same pitch range as well, so that you could compare them. In the end, I think this might be one of the things that we will find out if we get to testing in class and get to find out what our app really looks like when we test it with users. So it might work. We might find out. Then there's another question. Someone says Apple has this feature on the Stocks app when you use VoiceOver and select data comprehension on a graph. Was this an inspiration, and is this exposed for third-party apps at all? We also saw the tweets that I think you mentioned in the CocoaHeads Slack. And as we were building that, or as we were watching that, we had already finished building our app. So most of the development for this app was done at the end of last year. And by then, I think we hadn't seen the stocks implementation that Apple uses. I'm afraid, though, that the same that goes for the equation view that you saw in pages that are referenced in my talk, that it would be the same for this stock view. I would be happy to be wrong, because that would mean that we could use it and drop a lot of our Audiokit code, which is still, I think, the most feeble bit of code. There's a lot of state in there, and it's difficult to have that be nice and clean. So I would hope so, and I would hope if Apple delivers all of these features, then that would be great. That would mean that we don't have to build an app anymore. So not good for us, but good for our users. Then another question: was the math not spoken well if you use spellout attribute and or changed interpunction rotor settings? We did play around with it a little bit, but I think the thing with the spellout attribute or any way of just chopping up the function string in a string of characters has the difficulty of not including understanding of math in it. So you would still pronounce it like x2, and the example that you saw in the demo is we'd have x2 be pronounced as x squared, and x3 as x cubed. And that then also for both English and Dutch. And so we could do that. We could have some code in our code base saying if we have these characters next to each other, then please pronounce it as something like this. But that would be a lot of work. And the nice thing of Apple supporting MathML, albeit in a browser window, is that we don't have to think about that at all. We can just dump in whatever function we get and let them handle it. And that was really a nice thing, so we could focus on stuff like the audio rather than building a comprehensive math interpreter, which we also considered, but that wouldn't be a useful use of our time. Then I think there's another question by Carlos. He asks, have you thought about allowing the users to move their fingers left to right on the graph and then play the sound when they hit the intersection of the graph themselves? Yeah, that's one of the features that we hope to add in a future version, where you could just scrub on the graph and play the sound accordingly. I think from a technical perspective, the challenge there is in scheduling the audio correctly. So now our audio so our way of scheduling the audio is just a linear a way of going from left to right, calculating all the function values and scheduling the audio at the right time. When we go to scrubbing, we need to do an entire rollover of the way that we set up that code. So I don't think it will be trivial, but it's a very useful feature for end users. So we do want to do it. And hopefully we will get the time in preparation for the version 1.1 to actually make that happen. So yeah. Then I think there's clarification from Axel on his question about the base frequencies. So what he says is, I thought that another option would be to use the same frequency range so you get a moire effect at the intersections. I think that's a question or a topic that we might have to drag into the CocoaHeads Slack and discuss some more about, because I don't have an answer to that right now. So I would be interested to talk further with you to see if there's some insight there that could help us for our future versions. Yeah, and I think that's the questions I see now. So if there's no further questions, then thanks for your time again. I'll be in the CocoaHeads Slack. So if you do have any questions or you want to get in touch, then please find me on there. And with that, thank you for your time, and see you next time.